Hi. Last summer, you might have followed the Tour de France. The stages in the mountains, especially the downhill sections, are particularly intriguing. Cyclists zoom down mountainsides at speeds of up to 80 kilometers per hour, with a record breaking descent in 2019 exceeding 100 kilometers per hour. Now, these cyclists' high speeds are a result from the potential energy that they accumulate uphill. As they climb, potential energy builds up. During the descent, this potential energy transforms into kinetic energy, driving them downhill. So that means that while ascending, potential energy increases. So we can think of potential energy as a function that depends on your position on the mountain. Now, if you want to know how much potential energy you have gained while climbing the mountain, we simply need to take the potential at the top of the mountain and subtract the potential energy at the base of the mountain. The specific path taken during the ascent doesn't really affect the potential energy gained. As long as the cyclist reaches the mountain's peak, the potential energy remains consistent, regardless of the route. When dealing with line integrals of vector fields, a fascinating similar principle emerges. And in specific cases, the chosen path becomes inconsequential. What truly matters is the starting and ending points of the path that we follow. Vector fields with this property are called conservative vector fields, and we will see that they are defined by a potential. Consider, for example, the vector field F that you see on the screen. Let's integrate this field along a path from the origin to the point 1, 1. Now, initially, we will choose a straight line connecting these points. On the screen, you see the theorem that we will use to compute the line integral. The linear path that we will use can be parameterized as t times I plus t times j, where t ranges from 0 to 1. The tangent vector to this path is consistently equal to the vector 1, 1. Using the formula for line integrals, the one that you see on the screen, the line integral of f along this path r simplifies to the integral of t squared plus 2 times t squared from 0 to 1. And a very straightforward calculation yields that this gives us a result of 1. Now, remarkably, for this particular vector field, this result holds true for any path from the origin to the point 1, 1. Whether we traverse a straight line or a parabolic route, such as y equals x squared, the line integral computation using the same formula always gives an identical result. For example, the parabolic path can be parameterized as t times I plus t squared times j, with a tangent vector I plus 2 times t times j. On the screen, you see that the value of the line integral of f along the parabola is indeed again equal to 1. And so the path may vary, but as long as you start and end in the same point, the value of the line integral remains constant. Now, the reason why this phenomenon occurs is because f is the gradient of a scalar function phi. And in fact, the vector field f, the one that you see on the screen, is the gradient of the function x times y squared. And a vector field possessing this property is termed a conservative vector field. And the function phi is called the potential of the vector field f. Now, what is the analogy with the cyclists in the Tour de France that I talked about earlier on? Now, remember that the amount of potential energy gained while riding up the mountain was equal to the difference between the potential at the top and the potential at the base of the mountain. Now, here something similar is true. The value of a line integral in a conservative vector field is equal to the difference between the value of the potential phi at the endpoint of the path, and the value of phi at the starting point of the path. The independence of line integrals from the chosen path is not always guaranteed. Let's modify our vector field a little bit. Instead of f, we will use the vector field g, the one that you see on the screen. Integrating this new vector field along the previously used straight line gives us the integral t plus 2 times t squared from 0 to 1, which is equal to 7 over 6. Now, consider integrating the vector field g along the parabolic path. The result becomes an integral from 0 to 1 of t squared plus 4 times t to the power 4. And this is equal to 17 over 15. And so in this case, the path chosen to connect the 2 points really influences the value of the line integral for the vector field G. And this really contrasts with the behavior observed with the vector field F. That's all for now. I hope you enjoyed this video. I hope you learned something, and I will see you in class.